Hey, welcome to the 29th session of the Flipped Classroom for Calculus. We're going to play a little Mozart in the background. Hopefully it'll make this stuff easier to digest. This is the beginning of Chapter 4, Section 4.1, actually the first part. And it's about finding antiderivatives, indefinite integrals, initial value problems, and mathematical modeling. Okay, mathematical modeling we'll deal with in Part 2, actually. Definition of an antiderivative. We've talked about antiderivatives before. Basically, a function, capital F, that's important, of x, is an antiderivative of f of x if f prime of x equals f of x. In other words, an antiderivative is a function that if you take its derivative, it gets you back to the original function. And that has to be true for all x in the domain of the original function f of x. There's a set of antiderivatives because remember we can add c to them and there's infinite antiderivatives, and we would call that set the indefinite integral of f with respect to x. It's written as the integral sign, okay, of f of x dx. This is the integral sign here. F of x would be called the integrand, and dx would be the variable of integration. Okay, some terms you might want to know. An indefinite integral. The indefinite integral of f of x dx is just the antiderivative of x plus c. Example, the integral of x squared dx is x cubed over 3 plus c. Okay? If you're wondering how we got that, I'll talk about it on the next slide, but you might remember I asked you to come up with that rule, and basically you just add 1 to the exponent and divide by the new exponent, and add a constant c. How could you check the correctness of your answers for an indefinite integral? Simple. Take the derivative of your answer, and you should end up with the integrand x squared. Since the derivative of x cubed over 3 plus c is x squared, we're right. Yay! Remember, when I asked you to come up with that formula, okay, we said that the formula is if f prime of x equals x to the nth. In other words, if the derivative of some function is x to n, then the original function f of x equals x to the n plus 1 divided by n plus 1. That would be the antiderivative of this function x to the n. So you're just doing the opposite of taking the derivative. The question you always need to ask yourself for antiderivatives is what function has this, meaning the antiderivative, as a derivative. Okay? And you can always check yourself by taking the derivative of your answer, should get you back to the original problem. Alright, here's another sample problem. Let's say I want the integral, or antiderivative, of e to the 2x dx. Well, remember the derivative of e to the u is just e to the u times u prime. So to reverse or undo this, just divide by u prime. So the integral of e to the 2x dx is e to the u divided by u prime. We're letting u be 2x here, or e to the 2x divided by 2 plus c. Check it, okay? Take the derivative of e to the 2x over 2 plus c and see if you don't end up with just e to the 2x. Don't forget the c. If we're talking about an indefinite integral, there always has to be a constant of integration. Note, on page 335 in your text, there is a long table of integral formulas, okay? Some of these you will learn by heart, and some of them, nobody can remember them all, you can reference. Initial value problems. Okay, let's suppose you're asked to find the curve whose slope at the point xy is 3x squared, if the curve is required to pass through the point 1, negative 1. Okay, remember, when they tell you the slope at a point on a curve, they're really saying that that slope is the derivative. So what they're telling you is there's some function that has a derivative of 3x squared. Sounds like an indefinite integral to me. So what we're going to do is we're going to find the integral of 3x squared, or basically solve a differential equation, because if this integral, if 3x squared is the antiderivative, that means that it is the derivative of some function. So I'm really saying dy dx equals 3x squared, okay? Two ways to think of this. The integral of 3x squared dx is just 3x cubed over 3. Remember, add 1, divide by the new exponent, plus c, which equals x cubed plus c. You can take this derivative, and I bet you end up with 3x squared. Or another way to think of this is as a differential equation. Separate the variables, in other words, get dy equal to 3x squared dx. Take the integral of both sides. So I get the integral of dy equals the integral of 3x squared dx. The integral of dy is simply y, okay? Because y's derivative would be dy. Okay, so I get y equals 3x cubed over 3 plus c, therefore y equals x cubed plus c. Step 2, take your initial value, way up here, 1 minus 1. Insert x and y values of the given point into your answer, the antiderivative, to solve for c. So what I get is negative 1 equals 1 cubed plus c. c equals negative 2. So the equation, in this particular case, the unique solution to this problem would be y equals x cubed minus 2. Check by taking the derivative. Do we end up with the original function we had to take the integral of? Also, plug in 1 and negative 2 to see if that makes sense. So when I stick negative 1 into here, when I stick 1 into here, cube it, do I get negative 1 for my y? So therefore, we've shown that 1, negative 1 is not only a point on the derivative line, it is or tangent line, it is also a point on the curve. Makes sense. Here's what you need to do for practice. It looks like a lot, but these problems, some of them are very quick. Just read the instructions for each problem. We're going to go 340 to 341, numbers 1 through 46. Thanks, and have a good day.